Thank you for having me. Well, this talk is based on some joint work with Gabriela Geronimo and Juan Savia. And up to now, my research has been mainly focused on the development of theoretical results and efficient algorithms to be able to describe the common set of zeros of a system of n polynomials in n variables. And because of the applications, there's a lot of applications that have relatively equations that describe them with relatively few monomials, and because we are looking for efficient algorithms, is that there's some interest in the sparse polynomial systems. These systems are systems where the monomials that have coefficients that are non-zero are fixed, are preset. And to this fixed set of monomials that we are going to represent by their exponents, we're going to call supports and use this notation here, A1 to AM. My algorithms are not numerical ones, but symbolic ones. This means that we're going to describe the variety by using geometric resolutions, parametrizations by means of these geometric resolutions. And in the zero-dimensional case, when we have a variety that is definable over the rationals, if we have a linear form that sends different points to different values, then a geometric resolution is going to parameterize the variety using this polynomial here, this univariate polynomial, and a set of polynomials v1 to vn that they are chosen such that if we had the roots of q and we evaluate them in this vector here, we recover the variety v. This definition can also be extended to the equidimensional case. If we have a variety, an equidimensional variety of the dimension r, and for each irreducible component, we have a free maximal set of variables such that for each irreducible component this condition holds. Then we can get again to go to the zero-dimensional situation by inverting that set of maximal free variables. My algorithms are also probabilistic in the sense that they make some random choices of integers that if we chose them outside the Zariski clause proper set, allow us to get a correct result. And something to be said before I start, a difference between the generic square sparse case and the generic square dense case is that if we had as many polynomials as variables and with fixed degrees, and every possible monomial that can appear has a generic coefficient, then the common set of zeros is finite. But if we fix the monomials that can appear, then we can have components of positive dimension. For example, with this system here, if we factor the system, looking at which of these variables can be made zero, we obtain 5 irreducible components, and only one of them is a point. So we are interested in knowing when we're going to be able to find components of positive dimension in coordinate linear spaces, and of which dimension these components are going to be. A question to ask beforehand is in which parameters one wants to write the complexity of the algorithms. A combinatorial invariant that is expected to appear is the degree of a variety, somebody that I think everybody knows, but just in case, for an irreducible variety, the definition is the maximal amount of points in the intersection of the variety with as many hyperplanes as the dimension, as long as this set of these points are finite. And this number is achieved in the generic hyperplanes. And for arbitrary varieties, the definition of degree that I'm going to be using in this lecture is the sum of all degrees of each and every one of the irreducible components of the variety. So
even if they're different dimensions?
Yes, even if. Okay, I'm gonna use this notation a lot. I'm gonna call this way to the variety defined by the union of every irreducible component of the variety defined by a system F that has at least one point with all non-zero coordinates. That is the same thing as the Zariski closure of the set of all zeros of the system with all non-zero coordinates. So using that notation, then for a generic system with at most, for a generic system, either that variety is going to be empty, or in the case when the amount of polynomials is less or equal to the amount of variables, and when this condition here holds, then that variety is going to be an equidimensional variety of the dimension that one expects, the amount of variables minus the amount of polynomials, and degree this mixed volume, where these are the supports of the system, and this is the simplex repeated n minus m times that would be the support of the linear forms that one is going to be using to, for example, obtain the degree. And we can use this to give a probabilistic algorithm that generalizes an algorithm from Geronimo, Matera, Solonov, and Weinstein from 2009. That algorithm is for square systems, in this case for a system with at most as many polynomials as variables. We can compute a geometric resolution of the variety that I just defined with a complexity that, disregarding logarithmic factors, is polynomial in those combinatorial invariants there, the amount of variables, the amount of points in the supports, the degree of the variety, this other mixed volume here, and a combinatorial invariant that depends on fine mixed subdivision that we include in the input. There are several algorithms that compute this kind of subdivision, such as the one from Mizutani, Takeda, and Kojima from 2007. But they work really efficiently in practice, but they don't have an explicit computation of their complexity, and that's why we don't include them in the estimation.
What is the number? Is that the number of mixed cells, or what is that number?
This number actually is going to be the maximum of the norms of the primitive interior normal of all the mixed cells. Yes, and actually this other mixed volume comes from that subdivision, but
So
okay.
In the input is this defined mixed subdivision information?
Sorry?
So part of your input to the algorithm is
Part
not
of the-
just those
yes.
polynomials, but also this mixed subdivision.
Exactly, yes. And the basic idea is to take the variety, code it with n minus m generic linear forms. We then obtain finite points. We find a geometric resolution of those points using the algorithm from Geronimo, Matera, Solonov, and Weinstein that I was saying before. And then we lift those points to obtain the geometric resolution of this variety using a Newton-Hensel lifting, with precision the degree of the variety. So now that we have this algorithm, the idea is to be able to reduce the description of every component of the variety to that algorithm that I was just talking about. For that, I'm going to need some notation. This projection you can forget after this slide, but the rest are going to be appearing a lot. So Fi is going to be the system that we obtain by evaluating in zero the coordinates indexed by I and discarding the polynomials that vanish completely. Ji is the set of index of the polynomials that did not vanish. Pi is the projection to the coordinates not in I, and the last one is the set of supports of the system that can also be obtained by projecting with Pi the supports of the original system that are indexed by Ji. So if we have, the first result is that if we have an irreducible component of the variety defined by f, and we define this set IW as the set of all coordinates where all the points in W have a 0 coordinates, then the dimension of W can be written in using that IW and projecting the points, projecting W with P sub IW is not only a set of zeros of the system of this system, but it's an irreducible component of this variety that has at least one point with all non-zero coordinates. Using this and using the first lemma that that allow us to say that Fi is going to have at least one zero with all non-zero coordinates, if and only if we have that first condition, that blue condition on the supports, and using that for every reducible component of the Zariski closure of all zeros with all non-zero coordinates of Fi, and adding zeros in the coordinates indexed by I, then that is an irreducible component of the variety defined by f, if and only if we have this second blue condition on the supports. Those two blue conditions are only combinatorial. They are only on the supports. So they allow us to give a combinatorial description of the variety. Description that is going to be the union over all i's that fulfill these two blue conditions of adding zeros to these kind of varieties that we knew how to compute from the previous algorithm. And also a combinatorial expression for the degree as a sum over the same set I that fulfills those two blue conditions of the degrees of these varieties here. So using this, if we have a system in sparse representation with a fixed set of supports, first we find the second blue condition and this other condition here that is weaker than the first one but is easier to find and is also necessary. Then for every one of the sets I that fill us to those conditions, we found the geometric resolution of the of this variety, and in doing that we use the pre-processing that I was mentioning before, that in particular allow us to decide if this condition that I was mentioning before, the first one, is going to be true or not, because that first condition is equivalent to the mixed volume of the set of supports of this variety here, this system here completed with simplices, being 0 or not being 0. So adding 0 to the coordinates, to the corresponding coordinates and grouping by dimensions, we have a geometric resolution that describes each of the equidimensional components of the variety defined by f. And this algorithm is a probabilistic algorithm because of this step here, and it's going to have a complexity that this term is written in combinatorial invariants similar as the ones from before, but the first one, unfortunately, is exponential and cannot be disregarded because we can have an exponential amount of irreducible components. For example,
so what's new here is the n2 to the n? The
n to the n, yes.
That's what's new between what we had
yes. And as I was saying, if we look at this example, if for every two variables I choose one to make 0, one to make 0, and so on, then there's 2 to the n ways to do that, and that gives us 2 to the n components that they are not included in components of bigger dimension. So actually we can have, as I was saying, an exponential amount of components. The good news is that for systems such as this one, where all the supports are the same, we could present these kind of systems are called unmixed, and we could present a new reformulation of our characterization using that if this is the equidimensional component of the variety defined by f, then where you are going to be able to write it as the union over all i's that fulfill these conditions here of these linear spaces. And for these kind of conditions, we did get an algorithm to compute them in a polynomial time. So that gives us an algorithm to compute this kind of decomposition in a polynomial time.
So it's polynomial because you don't have to look at the, because all the a's are the same. You just look at one of them. Is that it?
Not because it's kind of like technical, but it was because we could in each step we could like limit the amount of we were adding like one polynomial at a time, and in each step we had a bound for the amount of components that could appear in it was the degree, and they were in each step we summed these things, so and at the end it was n times the degree and something else. So for the non-generical case, something that is worth mentioning is that unlike what happened with isolated roots, where in the generic, for a generic system with fixed supports, the amount of isolated roots is a superior bound for the amount of roots for an arbitrary system with the same amount of with the same supports. It's not that does not happen with the degree. The degree of an arbitrary variety with fixed supports can be larger than the degree of a generic system with the same set of supports. So we need a bound for the degree. In 2001, Teresa, Pardo, and Sombra presented this bound here for n polynomials in n variables. And just more recently, for the case of the square case, when we have n polynomials in n variables, we could improve a little that bound, because this new bound, it does not involve a union of the supports, but is only for square systems. And this bound is important to us because it's going to appear in the complexity of the algorithms. The idea, we heard this morning about witness set from the idea from Sommerset and Wampler. I'm not finding him, okay. About using sets of witness points to represent the irreducible and the dimensional components of varieties. For the non-generic case, the best that we could do was to find geometric resolution of what is called a witness points superset. This is a set of finite points that contains a set of witness points, but also can contain some points in components of bigger dimension. The basic idea is that if we add generic linear forms to our system, then it is known that every time I say it is known, I think that I'm reading too much Game of Thrones. Okay, it is known that if we take generic linear combinations and generic linear combinations of these polynomials, and in particular, if we take this kind of generic linear combinations where only the generic coefficients that we're going to be using are these ones, then all the isolated zeros of this system are also isolated zeros of this system here. So using that, having a system in sparse representation with fixed supports and the mixed cells in a fine mixed subdivision of the extended supports now, not only the supports, at first we find the geometric resolution of the zeros of a system with these extended supports, a generic system with these supports. Then we choose generic linear forms and use them to construct these systems here. And from the zeros from the original system J, we use homotopic deformation to find a geometric resolution of a finite set of points that contain all isolated zeros of this system. And clearing that from all the points that are not in the variety defined by F, we obtain a family of geometric resolutions that are geometric resolution of finite set of points containing witness set of points of every equidimensional component of the variety defined by F. And this algorithm is also probabilistic and has a complexity that is polynomial in the amount of variables, the amount of points in the extended supports, the maximum degree of the polynomials that hadn't appeared before, and in particular in the bound for the degree of the variety that I was presenting before. And that is all. Thank you very much.
Are there any questions for Luke?
Just wondering what's the range that you can practically compute? Like, if I give you a system of 48 variables and 48 equations, could you solve it at degree 6 or something?
The good thing about this kind of algorithms is that the complexity is in regards to the mixed volume. So if the mixed volume is small, if you have, for example, supports that are kind of like, I don't know, something like this, then maybe your degree would be really big, but the mixed volume is going to be really small. So the complexity is going to be small. But the bad news is that I'm learning to program right now. I haven't completely learned yet, so I haven't been able to write my algorithms in a computer. So I don't know how much time do they take. I can give you a theoretical description of the complexity.
Well, I think it uses tests. I mean, it's two different tasks to devise an algorithm and then implement it. If you ever try to work on both, you like the fact that they're counted twice. Yes, please.
And another question. You are always taking the union of the AIs with delta?
Yes.
The unit simplex?
For the non-generic case, yes.
In Cn.
Sorry?
Because you are looking for roots in Cn.
Yes.
And not C star n.
No, that was.
Look at the polynomials.
Yes, because we are using these polynomials here. So the support of these polynomials is the support of every polynomial and a simplex.
So you don't gain, you will not gain a better complexity by looking only for roots with non-zero coordinates. And maybe using Affine.
I don't know. I have to think about that.
Any other questions? Oh, I'm sorry, yes, please.
So, with respect to this algorithm, what is the difference with the algorithm geometry?
I can't hear you, sorry.
What is the difference between the algorithm on this slide and the one by Grégoire Le Cerf, Buenos, and Marc Justy for computing geometric resolutions in the case of reduced regular sequence?
This one is more intrinsic. I mean, I think this one takes into account the polytopes. Isn't that the difference?
I think so, yes. I think so.
What about the Justy-Le Cerf-Salvi algorithm? The complexity will be depending on the number of solutions, which we can bound like that, as well as the degree of intermediate varieties, which we could probably hope to bound like that. So wouldn't you be able to get the same kind of result at the end with their algorithm?
I'm gonna have to think. Maybe, maybe we can talk about it later. And
Are there any other questions? Okay, well, let's thank you.